Okay, so how would we approach this? Why don't you click and close, everybody? We got to dive into some deep calculus here. How would we approach this?
Well, you see that the one that says x equals 1,
Mm-hmm.
that one's kind of irrelevant, right?
Okay, that's good. The one in our piecewise function, the limit is not concerned with what the value of the function is when x actually equals 1. That is irrelevant, right? We only care about approaching, okay? So we want to know, first of all, for this limit to exist, what has to be true?
Left and right have to agree.
Okay, yeah, the limit from the left and the limit from the right have to agree, right? So how would we calculate this limit then? And if you were, for example, taking the AP test, this is how you'd want to organize your work. You'd want to do two one-sided limits and determine if they agree or not. If they do, then the two-sided limit exists and it has that value that they share. If they don't, it's a DNE because they two one-sided limits don't agree. So let's take, first of all, the limit from the left. So how would I write that? The limit of f of x. How would I write the limit from the left as x approaches 1? And then I'd put that superscript minus, right? From the negative, meaning from negative infinity, from the direction of negative infinity. Okay, well, let's evaluate that. That's the limit of what expression? Okay, good, because isn't this the part of the function that we're dealing with then? If we're approaching 1 from values less than 1, we're walking on this piece of the piecewise function, right? So we're evaluating that limit. It's the limit of 3x minus 1 as x approaches 1 from the left. Okay, what's that answer? 2, isn't it? I can evaluate that directly. Is this negative sign down here, is that important in evaluating the limit? No, doesn't matter, right? The fact that we're approaching 1 from the left, we're still approaching 1. So when we apply direct substitution, we're still plugging in 1, aren't we? Okay, so we end up with 2 for our answer. All right, so now let's look at the other one-sided limit, the limit of f of x as x approaches 1 from the right. And that would be the red piece of the function, right? So that's going to equal the limit of 2x as x approaches 1 from the right. And what's that answer? 2. So then what's the answer to my limit? Okay, because they agreed. Okay, 1 to 5, how are we doing? Good? Okay. Okay. All right, so back to the stuff we were looking at yesterday. So again, we always, when we are trying to take limits or evaluate limits, in calculus, a lot of times we'll say take a limit, but it just means evaluate the limit. We're going to always try direct substitution. One of three things is going to happen. Either it's going to work. I'm going to get a real number. I'm going to get a real number answer. And that could be 0, right? I'm done. That's it. The other thing that could happen is I could get an answer in the form some real number divided by 0. And we're done. That means the limit doesn't exist, and we're done for now. We'll get a little more specific very, very soon. So those are simple. Type 1 and type 2, really simple. You're either, you're done with the problem, move on to the next one. If you get an indeterminate form, like 0 over 0, or later on, when we start looking at infinite limits and limits at infinity and things like that, you could have other indeterminate forms like infinity over infinity also. Works the same way. Either if it's any kind of indeterminate form, then it means more work, and we have to move in and do some algebra to resolve the indeterminacy, and that's where we left off, right? The technique we looked at yesterday is called the dividing out technique. That's what this text calls it, and that's fine. I mean, that's a good way to describe it. So whenever you have a rational function, a polynomial divided by a polynomial, and direct substitution gives you an answer of 0 over 0, then guaranteed that's because there is a factor of the numerator and the denominator, a shared factor that has a 0 at whatever the value of c is, in this case, -3. So your job is to factor the expressions on the top and bottom and cancel that factor that's going to 0 on the top and the bottom. Remember what that does when we do that. So in this case, it'd be simple. We just factor that quadratic expression on the top and we cancel the x plus 3's. And algebraically then, we're trading our original function, this rational function, for a new function, which we could call g of x, which is x minus 2, which allows us to take the limit. And really what this corresponds to, and I think we had a pretty good handle on this yesterday, is we are filling in the hole, right? There was this original function that had a hole at x equals negative 3. We've traded it for a new function that fills in that hole. So now we can evaluate the limit using direct evaluation or direct substitution. Okay, that's our strategy. So really quick, why don't you try one of these? Try that guy just to kind of reinforce this. If you want to go to a board, you can. If you want to grab a whiteboard, you can. You can do it on paper. I don't care. Whatever you prefer. But give this one a try. Yeah, that's fine. Yep. Now, don't just assume that it's indeterminate either. What do you always want to try first? Direct substitution, because it may just work, right? This one doesn't, but you always want to try. Show me with your fingers what you got when you're done. Yep. Yep. Okay, let's take a look. So here's another thing I'll stress. It's really easy to get lazy with these and just start writing out ratios. But technically, and when I grade, like we'll do some paper and pencil tests. And I'm going to see your work on every test that we do. So it's all paper and pencil. I would actually probably take some credit off if you don't write it this way. If you just write out the ratio, that's incorrect. It's still a limit. Until we evaluate the limit, you have to carry that limit notation with every step, right? Because the limit of this function is equal to the limit of, or this expression is equal to the limit of what revised expression? What am I going to do on the top? Factor, and what does that factor into? And x plus 8, good. Right, but I haven't taken the limit yet. The limit of this is equal to the limit of that, right? We just manipulated the expression algebraically. And of course, what happens here? Yeah, I can, whoops, what was that? I can divide those out, right? I can divide those away, and so I end up with, I got a new function now. I still have to say limit though, because I haven't actually evaluated the limit until I do. Now, what is the answer? There. That's what your work needs to look like. Okay? Questions? That make sense? All right. Okay, so the next type of problem you might see looks a little different. This is not a ratio of rational functions, right? This is what you might call a complex function. Okay. not complex in the sense that it's involving the imaginary unit I, but complex in the sense that you're getting fractions over fractions. There's a couple ways to look at this. Now, if you think back to Honors Algebra 2, we did a lot of stuff like this where we talked about these kinds of problems as problems where you simplify them by simplifying the numerator into one big fraction, the denominator into one big fraction, and then flipping and multiplying by the bottom, right? That's one approach you could take, is just simplify the top, simplify the bottom, and divide. Let's look at that technique first. So if I'm going to do that, on the top, how would I simplify the top? When I'm adding or subtracting fractions, what do I have to do? Common denominator, right? So then I'm going to have the limit of 1 over x plus 10 times what? To get a common denominator, what do I have to multiply that first fraction by?
X plus 1.
No. I mean, what's my common denominator going to be in the top?
X plus 10.
X plus 10 times 10, right? You see why? The least common denominator is the least common multiple of all of the denominators. What's the smallest thing that the quantity x plus 10 and 10 would divide into? The product of the two, right? The smallest, simplest common denominator I can make with this factor and this factor is their product. Okay, give me thumbs on that. Is that making sense? Okay, so I mean, sort of. I think as we get to the end of this, hopefully it's a little clearer. So then I would have to multiply this one by 10 over 10. Now, if I want to get the same denominator, what do I have to multiply 1/10 by? X plus 10 over x plus 10, right? And on the bottom, I've just got this x, which is, I don't have to worry about that one too much, right? So what's that give me on the top then? If I multiply straight across, I get 10 over 10 times x plus 10 minus, on the top I get x plus 10 if I multiply straight across times 10 times the quantity x plus 10. Everybody see that's my common denominator now? Right? All over x. And so I could write the top using my common denominator as, how would I write the numerator there? I'm just looking at the top of the fraction. I've got my common denominator. What goes on top then? 10 minus, right? Because there's my minus sign. You're right, but how am I going to show me the steps? Minus the quantity x plus 10, right? Everybody see that? Because that's the stuff, that's all that stuff right there, right? That's what's going to sit above my common denominator. That's why we get the common denominator. Okay, now give me thumbs. Is that making a little more sense? Okay, why we're doing this? Okay, all divided by x as x approaches 0. Okay, so now we can simplify this another step. On the top, what are we going to get? Well, 10 minus the quantity x minus 10. Doesn't that just work out to be negative x when I distribute the negative sign and collect like terms? Right, the 10s are going to cancel. So I'm going to get the limit of negative x over 10 times x plus 10 divided by x as x approaches 0. And now I'll just flip and multiply by that bottom fraction, right? I've got a big fraction divided by a big fraction. And so we end up getting the limit of the numerator, and let's kind of color code this. So that one's going to be everything there, right? So the limit of negative x over 10 times x plus 10 times the reciprocal of the denominator. Everybody agree? Okay. Which gives us the limit on the top of negative x over 10 times x plus 10 times x. And now what can I do? Well, no, I mean, the whole point of this, and I guess I didn't mention this at the start, but I forgot to check this, but what would have happened if I would have tried to evaluate that original limit directly? I would have gotten 0 over 0, wouldn't I? Right? Okay, so now what can I do here to fix that? Cancel the x's, right? Okay, and I could have asked you at the beginning, what's the factor? So the problem is when x approaches 0, I get 0 over 0, right? So what's the factor that goes with x equals 0, right? It's got to be x minus 0, right? Remember that stuff we talked about yesterday? Let me see if I can grab that slide from yesterday. I just want to make sure this is a strong association for you. This factor theorem. Where was that? This slide. Where did I write that? I know I wrote that down. Right here. Write this stuff. X equals a is a 0 of the function if and only if x minus a is a factor, right? So x equals 0 would be a 0 of the function, right? That's what's causing the 0 over 0, only if x minus 0, which is x, is a factor of the top and the bottom. Everybody agree? Okay. So then if we go back to this example, well, yeah, there we go. There's the factor that's causing the issues, right? It's the offending factor is just the plain old x's. Those are the factors that go to 0 when x approaches 0. So we knew we had to be able to cancel those at some point, didn't we? Right? If we were going to get rid of this indeterminacy, we had to be able to cancel x's. So when x goes to 0, I don't have any factors on the top and the bottom that go to 0 anymore, right? So we cancel them. And I'm left with a new function. The limit at the top, I've got -1. On the bottom, I've got 10 times the quantity x plus 10 as x approaches 0. Okay, so when x approaches 0, that term right there just goes to 0, right? And what am I left with then? What's my answer? -1 over 100. Everybody see that? When I let that x go to 0, I just get -1/100th. Okay? Everybody see that? So that's one approach to this. One approach to these complex fraction problems is just to simplify the fractions right from the beginning. Okay, I'm going to show you what I think is a little bit better, simpler way. That always works, but let's take the same problem and let's use a trick called clearing the fractions here. Remember probably doing this with numbers back in Algebra 2. If I could just multiply both the top and the bottom by the least common multiple of x plus 10 and 10, in other words, what my common denominator was going to be in the last problem, right? Look what happens. I'm going to multiply both the top and the bottom by 10 times the quantity x plus 10. And let's see what happens here. I get the limit of. Well, what happens when I distribute that? I get, the first term is going to be 10 times x plus 10 over x plus 10. Everybody agree? When I distribute to that first fraction, that's what I get. Minus second fraction, I'm going to get 10 times x plus 10 over 10. Everybody agree? Okay. And let me maybe do that to remind us that all I've done is just distribute that to both fractions. Okay. On the bottom, I've got x times 10 times x plus 10. Okay, you see what this is going to do? Look what it does to these fractions. Up here on the top, it's going to cancel those factors in the first fraction and those factors in the second fraction, and it gets us there a little quicker, doesn't it? So I get the limit then of when those cancel, on the top I just get 10 minus, and let's track this minus sign. That minus sign is the same as that minus sign is the same as that minus sign, right? Minus, the 10's canceled, and so I've got the quantity x plus 10 over my denominator, which would just be 10x times x plus 10. Well, we're almost done, right? Now, if we just distribute the negative sign, this ought to look pretty familiar. We get the limit of negative x over 10x times x plus 10 as x approaches 0. And here's where we can cancel those x's. Okay? Let me remind you here, because even in calculus, this is a common mistake. I can only cancel things vertically if they are like factors. I can't cancel things that are being added or subtracted, only things that are being exclusively multiplied by other factors, right? So what I mean by that is, I'm going to scroll down for just a second, take a little interlude. Like this I can do. Those guys cancel, right? But I can't cancel those x's, right? You see that? Because this x is not a factor, it's a term. It's being added to something on the top, right? So I can't do that there. Everybody give me thumbs on that. Does that make sense? Okay, just quick reminder. And then now I can take my limit. If I let x go to 0, well, let's just write this down real quick. If I let x go to 0, that term goes away and I get my negative 1/100th, just like I did before. But to me, that way's a lot quicker, right? You don't have to deal with so many big fractions. You clear the fractions right away. After one step, we no longer have fractions on the top. I think that's the preferred method. Yes, you just distribute through top and bottom the common denominator of all the fractions. Yeah. Okay. Make sense? Okay, try one. Try that one. Yep, right. So you're going to distribute through 5 times the quantity x plus 9. Yep. Here, while you're doing it, I will type it up on math type so it looks really good. We'll check, see if we get the same answer. And of course, we'd want to try it first, but if I evaluate this at -4, can everybody verify that it becomes 0 over 0? So we do have to do more work on this. You need another minute or two? How am I done? A little bit longer? Okay, good, because I got to finish this up. Oh, that's just a work of art. That's so nice.
I don't have a common denominator. Multiply them both by the same thing. But if I just multiply that multiply.
Are you doing the or what does it sound like?
Well, not even really.
Okay, should we have a look? Let's see how we're doing here. Okay, so what's our first step? Okay, yeah, so the least common multiple of the denominators is what? What am I going to multiply the top and the bottom by? There you go, 5 times x plus 9, right? Okay, good. And so if I do that, if I distribute on the top, then that's just going to give me, well, that, isn't it? Right? If I distribute this to each of those fractions, here's what I get on the top of the first fraction, and here's what I get in the numerator. Here's what I get in the numerator of the second fraction, right? Okay, and I get cancellation. The x plus 9s cancel in the first fraction, and the 5s cancel in the second, leaving me with, and on the bottom, I've just got this product of some stuff, right? Nothing to simplify there. Okay, so doesn't that just leave me with that, right, when I cancel? Okay, pretty good? Okay, if I distribute the negative sign and combine like terms, doesn't that just give me that? Right? Okay, now what has to happen here? Looking at the original problem, before we started anything, what are the factors based on this? What are the factors that have to cancel eventually? X plus 4, right? Because remember, if x equals negative 4 is a 0, then x minus negative 4 or x plus 4 is a factor. So we already know eventually I have to be able to cancel x plus 4s in the top and the bottom, right? So we're kind of looking for that to happen. Well, where's that going to happen? There's an x plus 4 in the denominator. Where is it in the numerator? Well, I could multiply the top and bottom by negative 1. That's fine. I treat both the top and the bottom equally, multiply by 1. Or what could I factor out of the top? Negative 1. If I factored out a negative 1, undistribute a negative 1, don't I just get that? Right? Everybody see? And now there I get my x plus 4s that I knew I had to have. I knew those had to cancel. They had to, right? Because that's how the indeterminacy is going to go away. And so then I end up with the limit of this simple function. On the top, I'm left with a negative 1. On the bottom, I've got a 5 times the quantity x plus 9. And if I evaluate that directly, I just get a number, negative 1/25th. Right? Okay, makes sense? Oh, well, okay, but I mean, well, that's all. I mean, simple, dumb little math mistakes. I don't care about those. As long as the concepts are there, if you're following the right procedure and you're understanding the process, that's all I care about. On a test, if you went through all that work on a test and you made one little goofy error at the bottom, you might even get full credit. It's going to be virtually full credit, if not full credit. Okay. All right. So the last thing I'm going to show you one other technique today. So what have we got now? Think about this. We've got 2 techniques in our tool belt here. If we have a rational function, we just factor the top and the bottom and cancel factors. That's pretty easy. If we've got complex fractions, we've got to go a step further, right? Complex fractions, in order to make it look like a rational function, we have to clear the fractions. And then eventually, look what happened when we did that, though. Eventually, we got what looked like a rational function, and now we have to just cancel, right? Yep. Oh yeah, when are we out of here? Like in 4 minutes? Okay, this is a good place to stop then. Yeah, let's talk about that last one. We'll do rational functions next time. We're not going to get through them anyway. And let's talk about that last one. That's a good breaking point. Okay, so let's find that guy. It was not that. What did I do with it? Right there. Ooh. Okay, we can do it. Okay, so what about this then? Suppose a spaceship of length L naught is traveling, we have sub-zero, we just say naught in physics and math, is traveling at a high rate of speed, v, relative to an observer. To the observer, the ship appears to have a smaller length given by the following formula. This is called Lorentz contraction. And this really happens, by the way. I kind of object to this terminology they use here. This must not have been written by a physicist because it doesn't appear the ship actually does have a smaller length. It does shrink along the direction of travel and it rotates a little bit too. We won't worry about that. So where c is the speed of light. Well, what do they ask us to do here? They ask us to plug in some values of v, right? Like if I did half the speed of light, that would just be 1/2 c that I would plug in, right? If you're traveling half the speed of light, I would get L of 0.5 c is equal to my original length times the square root of 1 minus 0.5 c squared over c squared. 0.5 c squared is just 0.25 times c squared, right? So the c squareds would cancel, and I would end up with L naught times the square root of 1 minus 0.25. So it's this, it's L naught times the square root of 0.75, which is a fairly, it's a small number, but it's bigger than 1/2. Okay, I'm going to get some, see what I'm saying? Right. Okay. But what's tricky here is what's going to happen as V approaches C, and that's what we'll talk about first thing on Monday after a break. How about that? And maybe we'll spend a little more time. I was rushing too much, maybe a little bit too. So we'll talk about this one. Don't worry about the due date. If you do all of them except that last one, don't sweat it. We'll talk about it on Monday. It's a kind of a complicated property of Lorentz contraction that it appears to rotate a little bit.
Always rotate the same way.
Yes, it always tends to rotate a little bit towards the observer. Yeah. You too.